Hi there, this is your Unit 6 practice test. For full credit, you must have the graph accurately drawn. You are able to use your calculator for this. The area being considered needs to be shaded and the integral must be set up appropriately. Organization and neatness in your work will be a factor in grading. If not expressed as a fraction, your answer must be accurate to at least 3 decimal places. Okay, so for these problems, there are 3 groups: area, solids of revolution, and cross-sections. And then underneath cross-sections, I went ahead and included a subsection just for you to make sure you've memorized your area formulas that will be used in finding the cross-sections. Okay, so this first one, area, we're asked to find the area of the region between the graphs of y equals 3x cubed minus x squared minus 10x and y equals negative x squared plus 2x. Okay, so we're going to go ahead and plug that into our calculator as follows. Okay, 3x cubed minus x squared minus 10x and negative x squared plus 2x. Okay, once you have that plugged in, you'll go ahead and hit graph. Well, my window, just so you know, is negative 10 to 10. Okay, but then we're going to graph it, and you'll get a graph like this one. Okay, and we're going to go ahead and sketch that. Okay, now when I say that your graph needs to be accurately drawn, it doesn't have to be perfect, right? We aren't in art class, but it does need to be accurate, right? So if something's going through the origin, it needs to be showing up on your paper as going through the origin. And so that's that cubic graph that we see here. And I'm going to go ahead and label that y equals 3x cubed minus x squared minus 10x. And then my quadratic crosses, comes up, goes through the origin, and then circles back down. And this is my y equals negative x squared plus 2x. So 3 intersection points. And I'm going to go ahead and shade in, right? The area being considered needs to be shaded. I'm going to shade in the area bounded by those graphs. So I have one here and one here. Okay, since we have 2 regions, that's going to be 2 integrals being added together. Okay, so my first integral is going to go from this first intersection point to the second intersection point. I'm going to go ahead and calculate those intersection points. 84s you hit second calc, 89s you hit F5, and it's number 5, your intersection. Okay, first curve, second curve, we just hit enter twice because there are only 2 curves plugged into our calculator. My lower bound, I'm going to go to the left of that. My upper bound, I'm going to come to the right. And my first intersection point is at negative 2, x equals negative 2. Okay, my second intersection point, same thing, first curve, second curve, left, right, is at x equals 0. X equals 0. And in this case, when I draw in my representative rectangle, and again, I recommend drawing that in, okay, I have upper minus lower, which is my, upper is my cubic, so that's the 3x cubed minus x squared minus 10x, minus my lower, which in this case is the quadratic, which is negative x squared plus 2x dx. And then we're going to add to it my second integral, which goes from 0, that second intersection point, to the third intersection point. Same thing. Intersection, first curve, second curve, lower, upper. My third intersection point is at x equals 2. And then same thing, draw in your representative rectangle. My upper in this case sits on the quadratic, which is the negative x squared plus 2x, minus my lower, which in this case sits on the cubic, 3x cubed minus x squared minus 10x dx. Okay, so I'm going to take all of that, plug it into my calculator. 84s, you'll go to your home screen, you'll hit Math 9, which says F in int. 83s, you're going to go to your home screen, hit Math 9, which is F in int. 89s, you're going to hit F3, which is your calc, and then 2. 84s is going to look like an integral, so plug it in like it looks. Make sure to watch parentheses and negatives. 83s and 89s, you're going to go ahead and follow along with me. We plug in our function, which is this 3x cubed minus x squared minus 10x minus parenthesis negative x squared plus 2x parenthesis comma x, which says dx, comma my lower bound, which is negative 2, comma my upper bound, which is 0, parenthesis. And then we're going to add to it our second integral. So same steps. Negative x squared plus 2x minus 3x cubed minus x squared minus 10x, comma x for dx, comma lower bound, which is 0, comma upper bound, which is 2. When you hit equals, you get 24. Okay, so that's how we find area. Remember, area is about as basic as it gets, upper minus lower of our shaded region, and our bounds are x bounds, right, because we're always doing it with respect to x. And so you find your intersection points, or if they're given to you, you use the given bounds. Okay, number 2, we're looking at solids of revolution. Asked to find the volume of the solid generated by revolving the region bounded by these graphs. So I'm going to go ahead and take a moment and plug that in. We have our y equals x squared, which is just a quadratic. We know that, but it's helpful to see it, potentially. Okay, so I'm going to go ahead and sketch that in. Y equals x squared. Okay, and then y equals 0, which is my x-axis. X equals 0, which is my y-axis. And x equals 3. So x equals 3, which is a vertical line. I'll go ahead and sketch it here. X equals 3. And so it's this region here. And in A, we're going to be revolving that around the line x equals negative 1, which is this vertical line out here. X equals negative 1. It's going to be my axis of revolution. Okay, so equation is pi integral a to b of big R squared minus little r squared. In this case, because our axis of revolution is parallel to the y-axis, this is going to be dy, which makes my bounds in terms of y. So I'm going to be looking at my lowest y and my highest y. My lowest y is down here at 0, and my highest y is whatever that point is up here, right, where x equals 3 hits my y equals x squared. Well, that's going to be at 9, right, because 3 plugged in here, the intersection, x equals 3, 3 squared is 9. Okay. So my big R is the distance from the axis of revolution to the furthest point of my shaded region. Little r is the axis of revolution to my closest points. This is big R, this is little r. Okay, and then upper minus lower. My upper of my big R sits on the graph, x equals 3. My lower of my big R sits on this graph, which is x equals negative 1. My upper of my little r sits on this graph, which is y equals x squared, but I don't want to put in x squared here. If I put in x squared, I get x squared with respect to y. Right? We want these to be the same variables, so I'm going to go ahead and turn this into an equation in terms of y. I'm going to take the square root of both sides, and anytime you take the square root, make sure to do plus or minus. And then this little r sits on the positive side of that quadratic, right? That point sits on the positive side as opposed to the negative side. And so when we plug this into our equation, we're going to be using the positive root y for my upper. And my lower still sits on x equals -1. And that's something you should see for all of these problems. Your axis of revolution, whatever it happens to be, should show up in both your big R and your little r. It might be at the back or it might be at the front. It might be the upper or the lower. That all is connected to where your shaded region is in relation to the axis of revolution. But your axis of revolution, in this case -1, should show up in both your big R and your little r if you set up your integral correctly. And so then we're going to go ahead and plug this in. Before I plug it in, I'm actually going to simplify it up a little bit. 3 minus -1 is the same thing as plus a positive. So this is 4 squared, which is 16 minus, then I'm going to go ahead and do root y plus 1. Right? Minus a negative is plus. dy. Okay, and so we're going to go ahead and take that, plug it into our equation. Or sorry, plug it into our calculator. And we are at 16 minus square root y plus 1 quantity squared, comma y for dy, comma my lower bound, which is 0, comma my upper bound, which is 9. And we should get 117 pi over 2. Okay, B, we are doing the same graph, so I'm going to go ahead and re-sketch this down here. Y equals x squared. Y equals 0, x equals 0, x equals 3. Shaded region. But in this case, my axis of revolution is y equals 0. It's the x-axis. So I'm going to go ahead and draw in my big R from the axis of revolution as far as I can go, and my little r from the axis of revolution as close as I can go. And in this case, the axis of revolution is part of our shaded region, so there's no distance for our little r. And I'm going to go ahead and set this up. Pi integral big R squared minus little r squared d. And in this case, our axis of revolution is parallel to the x-axis. It's actually the x-axis itself. But since it's parallel to the x-axis, this is going to be dx. And so my bounds are going to be my x bounds, my smallest x in the shaded region, which is at 0, and my largest x in the shaded region, which is at 3. Okay, so big R, the upper sits on y equals x squared, minus the lower sits on y equals 0. And little r, upper and lower are the same place. There is no distance there, right? 0 minus 0 is 0. And I'm going to go ahead and again simplify this up a little bit. Pi 0 to 3 of x squared minus 0 is x squared. X squared squared is x to the 4th dx. Okay, and so when you take that and you plug it in, you should get 243 pi over 5. C, we are revolving the same region around y equals 10, so I'm going to go ahead and sketch that graph in. Actually, because I ran a little bit out of room, I should have slid this initial graph over slightly. I'm going to go ahead and sketch it down here. So we have our y equals x squared, our y equals 0, our x equals 0, our x equals 3, our shaded region. And in this case, I'm revolving my axis of revolution, or I'm revolving my region around the axis of revolution, y equals 10. And y equals 10 is up here. Y equals 10, it's my axis of revolution. Okay, so let's go ahead and set this up. We have pi integral big R squared minus little r squared d. Okay, since my axis of revolution is y equals 10, which is parallel to the x-axis, this is going to be dx. So my bounds are going to be the largest and smallest x in the shaded region. Smallest x is at 0. Largest x is out here at x equals 3. My big R from the axis of revolution as far as you can go through the shaded region. Little r from the axis of revolution to the closest point of the shaded region. Okay, so my big R upper sits on y equals 10. My lower sits on y equals 0. Little r, my upper, sits on y equals 10. My lower sits on y equals x squared. And again, before I plug this in, I'm going to go ahead and simplify it up a little bit. 0 to 3. We have 10 minus 0 is 10 squared, which is 100, minus 10 minus x squared squared dx. Okay, so then we're going to go ahead and take that, plug it into our calculator. 100 minus the quantity of 10 minus x squared squared dx from 0 to 3. And we should get 657 pi over 5. Okay, last one, same region. One more sketch, y equals x squared. X equals 3. Y equals 0. X equals 0. Nice shaded region. In this case, my axis of revolution is x equals 0, which is that y-axis there. Okay, so big R from the axis of revolution as far as you can go through the shaded region. Little r from the axis of revolution as close as you can go in the shaded region. Okay. And then we're going to go ahead and set this up. We have pi integral big R squared minus little r squared d. And then since this axis of revolution is parallel to the y-axis, it's the y-axis itself, we're going to go ahead and do dy, which means my bounds are going to be my y's, lowest y, highest y. Lowest y is down here at 0. Highest y is at that point where x equals 3 hits y equals x squared. Well, where does x equal 3 hit y equals x squared? It's when 3 squared equals y, which is 9, right? Plugging in 3 here, 3 squared is 9. So my that's my upper bound, which is 9. Okay, big R, distance from the axis of revolution as far as you can go. My upper sits on the graph, x equals 3. My lower sits on the graph, x equals 0. Little r, upper sits on the graph, y equals x squared, but I don't want to put x squared in here because it's dy, so I need to turn that into an equation with y, so plus or minus square root y equals x. And this particular portion of that quadratic is the positive root y as opposed to the negative root y, which is over here. So my upper sits on positive root y minus my lower, which sits on x equals 0. And again, I'm going to go ahead and clean this up a little bit. 0 to 9. 3 minus 0 is 3 squared, which is 9. Minus root y minus 0 is root y squared, which is y. Okay. So we're going to go ahead and take that, plug it in. We get 9 minus y dy from 0 to 9. And we should get 81 pi over 2. Okay, last sections. We've done area, we've done volume, cross sections. Okay, number 3, the base of a solid has a region bounded by x squared plus y squared equals 16. Find the volume of the solid whose cross sections are semicircles perpendicular to the x-axis. So I'm going to start with graphing that. I know that that's a circle with a radius of 4, because 4 squared is 16. If you didn't identify that immediately, you would solve for y to put it into your calculator. Right, so I'm going to go ahead and take this up here. We'd subtract the x squared over, so we'd get y squared equals 16 minus x squared. And then we'd square root both sides. Anytime you take a square root, you do plus or minus 16 minus x squared. Okay, and so that's what you'll plug into your calculator. If you didn't see it was a circle, immediately you'd put in your square root 16 minus x squared and your negative square root 16 minus x squared. And your calculator would generate the circle for you, so you could see what you were looking at. There's our circle. Okay. We are going to be finding the volume of the solid whose cross sections are semicircles perpendicular to the x-axis. So when I draw in my representative side length here, it's going to be perpendicular to the x-axis. So I'm going to go like this. Okay. And this is a semicircle, so coming up out of this paper, right, 3D is a semicircular cross section. So cross-section formula, we do a to b of whatever our formula happens to be. With a semicircle, it's 1/2 pi r squared d, and then since the cross-section is perpendicular to the x-axis, we're going to be doing dx, and our bounds are going to be the lowest and highest x in our shaded region. Our lowest x is -4, our highest x is 4. Okay, my r is found from my representative side length here, right? So if I have my little semicircle coming up out of here, and it's a little hard to visualize, but if you can picture that semicircle sticking up out of the paper, right? This upper minus my lower is the diameter of my circle. So my upper is going to be the positive, which is root 16 minus x squared, minus my lower, which is the negative portion of that circle, 16 minus x squared. But that upper minus lower is my diameter. My equation is 1/2 pi r squared. R is my radius, and so I'm going to go ahead and take my diameter and divide by 2. Okay, and so that's going to allow me to find the volume. So we're going to go ahead and go home. We have 1/2 pi, and then our r, parenthesis, and then parenthesis again. That way our two square roots both end up in the numerator. So we're going to go ahead and go square root 16 minus x squared, 16 minus x squared, and then we're going to go divided by 2, end parenthesis. That end parenthesis closes off my radius, and I'm going to square my radius. Then comma x for dx, comma -4, which is my lower bound, comma 4, which is my upper bound. And I should get 128 pi over 3. Okay. Number 4, we have the base of a solid is a region in the first quadrant enclosed by the graph y equals 2 minus x squared and the coordinate axes. So I'm going to go ahead and draw that. Y equals 2 minus x squared is a quadratic. and the coordinate axes. And then it's in the first quadrant, so this is my shaded region here. We're going to be calculating the volume of the solid whose cross sections are squares perpendicular to the y-axis. So I'm going to go ahead and draw in my representative rectangle perpendicular to the y-axis, and if you wanted to, you could sketch in your square, right, sticking up out of that paper. Okay, so cross sections, we have integral a to b of whatever our formula is. For a square, it's s squared. D, this is perpendicular to the y-axis, so we're going to be doing dy. So we're going to be looking at my lowest y, which is down here at 0, and my highest y, which is at that point, which is y equals 2. My squared is my upper minus lower. My upper sits on the graph 2 minus x squared. But we're taking our integral with respect to y, and so I don't want to plug in 2 minus x squared, right? That mixes my variables. I want to instead turn this equation into terms of y. Okay, so I'm going to go ahead and take this. Let's rewrite it first. Y equals 2 minus x squared. I'm going to go ahead and subtract the 2 over. Y minus 2 equals negative x squared, and then I'll divide the negative. 2 minus y equals x squared. And then take the square root, but remember, anytime you take a square root, make sure to do plus or minus. This point here, this upper point, sits on the positive part of our quadratic. Okay, and so this is my square root 2 minus y. Okay, and then minus my lower, which sits on the x-axis, sorry, on the y-axis, which is at x equals 0. Okay, and so that's what we're going to plug in. I'm actually going to clean this up a little bit. 0 to 2 of square root 2 minus y minus 0 is just square root 2 minus y, which that squared is 2 minus y. Okay. So we're going to go ahead and go to our home screen. Calculate that integral. We have 2 minus y dy from 0 to 2, which is 2. And there we go. Those are our cross sections. Okay, so this last section is just making sure you know all of your formulas, because you are responsible for knowing all of them. Area of an equilateral triangle is root 3 over 4 s squared. Area of a square is s squared. Area of a triangle is 1/2 base times height. Rectangle is base times height. And a semicircle is 1/2 pi r squared. And I might include a note on the semicircle for myself if this were mine to study for the test. Don't forget to divide by 2 on your semicircle, right? Because remember, with the semicircle, we were finding the whole diameter, and we want just the radius. For just the radius, we're going to divide by 2.